Welcome all. Today we are exploring into a critical topic, that is choosing the right power rating for your motor in a specific application. This decision is essential for achieving both economy and reliability. The power rating of a motor, often measured in horsepower or kilowatt, is like the heart of your machinery. Selecting the correct power rating is essential to ensure your system operates optimally, balancing cost effectiveness with reliability. First, let's explore the consequences of using a motor with an insufficient power rating. When a motor lacks the necessary power for a specific task, the motor struggles or fails to start and drive the load, resulting in inefficient performance. Frequent damages and shutdowns occur due to overloading of the motor and power modulator. This leads to costly downtime and reduced reliability. Now, consider the other side, using a motor with excessive power. Overrated motors come with higher upfront price tag. You end up paying more for power capacity that you may not need. Operating an overrated motor at less than its full capacity results in energy inefficiency. It consumes more energy than necessary, leading to increased operational cost. In conclusion, the power rating of a motor is a critical decision that shouldn't be taken lightly. The consequences of using an inefficiently rated motor include inefficiency, frequent breakdowns, and reduced reliability. On the other hand, opting for an overrated motor results in unnecessary initial expenses and energy wastage. To make the right choice, carefully analyze your application's requirement, considering factors like load demands, duty cycles, and safety margins. Consult with experts and refer to manufacturer guidelines to ensure a precise match between the motor's power rating and your application needs. Remember, a well chosen motor power rating not only ensures optimal performance but also contributes to long term cost saving and reliability. Now, the determination of motor rating is broadly classified into continuous duty, fluctuating loads, short time, and intermittent duty. At first, continuous duty. The selection of motor capacity for such a drive is simple if we know approximately the constant power input required by the machine. In order to select a motor for a rating equal to the known power input requirement, one may be sure that this rating is the maximum permissible with respect to heating because the manufacturer designs and rates it so as to maintain maximum utilization of the material used at rated output. For continuous duty at constant or slightly varying load, a motor is selected from a relevant catalog for a capacity corresponding to the power required. Although losses during starting are greater than those under rated load, they may be neglected because starting under continuous duty is very infrequent and practically no influence on motor heating. Next, we have fluctuating loads and intermittent duty. This method is based on approximation that the actual variable motor current can be replaced by an equivalent current which produces same losses in the motor as actual current. The equivalent current is determined by the equations as shown. As we know, motor loss consists of two components. One is the PC constant loss, which is independent of load, and the another one is core loss and frictional loss PCU, which is a variable loss dependent on load copper loss. For a fluctuating load consisting of n values of motor currents I1 till In for a duration of T1 till Tn respectively, the equivalent current I equal is given as such. After I equivalent is determined, a motor with next higher current rating from commercially available rating is selected. Then this rating is checked for its practical feasibility. Next we have short time duty. In short time duty, time of motor operation is considerably less than the heating time constant, and motor is allowed to cool down to ambient temperature before it is required to operate again. A motor with continuous duty power rating can be overloaded by a factor K greater than 1, such that the power rating becomes K into PR and the maximum temperature rise reaches the permissible value theta. When the duration of running period in a duty cycle with power KPR is TR, note that theta SS is the steady state temperature rise which will be attained if the motor delivers a power on continuous basis, whereas the permissible temperature is also the steady state temperature rise attained when the motor operates with the power PR on continuous basis. Next we have intermittent periodic duty. During a period of operation, if the speed changes in wide limits leading to changes in heating and cooling conditions, methods of equivalent current, torque, and power described previously cannot be employed. Let us consider an intermittent load where the motor is alternatively subjected a fixed load of duration Tr and standstill condition of duration Ts. As the motor is subjected to a periodic load, after the thermal steady state is reached, the temperature rise will fluctuate between a maximum value and a minimum value. For this load, the motor rating should be selected such that theta max is less than or equal to theta permissible, that is, the permissible temperature rise of a motor. Thank you.